So we can start.
Good afternoon, everybody again. We'll be moving to the workshop section of the conference. The first section of the two sections discussing green communication. Mr. Afron Patrick from Ukraine will be the first one to discuss, and the floor is yours.
Thank you. So, I'm Tom Patrick. I'm a PhD student and lecturer assistant of Computer System and Fields Department of Ukraine National Space University in Kharkov. The topic of my report is related with parameterization of FPGA projects. And sounds like a Scalable FPGA-based project via static and dynamic parameterization technique. So, at the start, I want to define some understanding of some terms. For example, the parameterization. The parameterization is a process of selection of the project parameters which allows to change its characteristic result to design. So, it seems it's clear, but in case of FPGA project, it means that we can create one, maybe some model that can be used or reused in another project with another requirements without redesign. So, our research of a variety of possible variants of parameterizations shows that all types of parameterization can be classified to static parameterization and dynamic parameterization. So, the FPGA language based on other language, and in the other language there is the static parameterization as well. So, the static parameterization is a parameterization of projects at the time of development, maybe before the compilation. And dynamic parameterization is a parameterization at time or at run, maybe, during the operation. The example of static parameterization we can find at some libraries in the development environment, for example, in the Quartus from Altera or in IC from Xilinx. For example, some components, basic components, that can be adopted according to the requirements of the project by assigned of different values to different parameters. So, this is parameterized models, and this process is a parameterization. It's clear. But in case of dynamic parameterization, it's more complicated. But, for example, the dynamic parameterization can be described maybe an example of some simple counter that have a preset input of the start of count. And we can assign some values to this input during the operation. And it will be the start value of counter. It's a dynamic parameterization. Typically, all devices with dynamic parameterization can be organized in the following way. Few, or maybe one multiplexer and demultiplexer, and some number of parallel and dependent implementations of different functionality. that can be selected by input signals. So, this approach requires computational resources, but allows to change some functionality of some devices during the operation without the recompilation or rebuilding of project and reinitialization of FPGA devices. So, in most cases, the parameterization at all can be classified on the functional and structural. The VGL language, or our study of VGL language, shows that there are three possible statements or some language constructions that provide the ability of static parameterization. There are generalization, constant, and some parts of generic map statement. The throw parameterization, it's a throw, means that all parameters in this project or in this model should be passed to all nested components or used components in this component. It's may be realized using this functional parameterization. But the most interesting is the structural parameterization, and the statement of visual language allows it by means of few statements, iterate and forgenerate. It allows to produce some components that can be parameterized at time of design in order to reach the parallelism or some parallel implementation. So, these features of hardware description languages, in case of visual language, allows to control amount of FPGA resources. So, all mentioned features allows to propose the multiparametrization technique. Multiparametrization includes both the parameterization of way of implementation and parameterization of all functions. And providing of these parameters to all levels of the composition of the project. To understand this idea, let's consider this example. For example, we have some little chip. Let's assume the antenna is one chip. And we have some project. But this project requires for some amount of resources larger than we have in case of this chip. But redesign of this project allows to fit this project to this chip. But the development using multiparametrization allows to create some project that can be parameterized according to the available resources. And in this case, we can fit this project to any, or maybe just any, packages, the FPGA packages. In this case, we have, for example, another chip with another resources, and the same project with multiparametrization can be parameterized in the following way to be placed in these resources. In this picture, the horizontal line associated with the FPGA resources, and the vertical with the time of computation. The higher, the longer. The shorter, the faster. So, the short means the highest performance. It's the main idea. To reach this idea, we propose two techniques. The first is a Multiparametrization technique that allows to design such projects and support such way of parameterization and control of resources. So, there are four steps. The first one is the finding of the boundary values of some input buses, for example. Second is the finding of paths that can be parallelized. And if the algorithm cannot be parallelized, it doesn't matter, because even the arithmetical operation can be parallelized. For example, addition or multiplication and so on. Next step is a definition of number of parallel elements inside of this component as independent parameters, static parameters. And the manner of operation, parallel or sequential too, as a parameter. And the last step is providing this information or providing these parameters to all used components in this component. So it's a strong parameterization. Okay, let's consider the example of implementation of this technique. My research goal related with the electrical impedance tomography accelerator, FPGA-based accelerator. This is some variance of parameterization of this model. The basic functionality of this model is a multiply accumulate operation. In this picture, there are two variants of parameterization with one channel, two channels, 3 channels, 4, 5, 6, 7, 8, 9, 10, and so on. So, the one project developed using this technique provides the ability of parallelization, and it's interesting. It's some peculiarity of this project, the parameterization of adder, because in all cases this parameterized adder will be no longer than elements in nodes, where L is the logarithm of n, rounded to higher level. So it doesn't matter, but in case of large parameterized variants, there are a lot of resources required to implement this project in FPGA. Another important question is how to calculate or estimate the required resources. So, we propose another technique to find the required amount of the resources. The first is the building of model of the developed component. So, this model should include some important structure of this component. Next follows the evaluation, experimental or maybe analytical evaluation of the requirements of the resources of the different parts of these parts of this component. So, if we know the relations between the parameters and resources of different parts, we can, using the model of our component, create some analytical formula or formulas of dependence of the resources for each possible variant of FPGA resources. For example, in case of certified data passes, in my accelerator, we have big number of multipliers, adders, and RAM components. And according to this technique, we can calculate the number of resources using the analytical formula. And we can compare it with the report of the software tool, of the platform tool. And it will be the same. So, for example, how it works? We have, for example, 2 multiplied by n elements for adders. And according to this formula, we can find the needed number of logical elements. It's the same with the number of implemented multipliers. It will be 70. And so on. So, it's a simple example because here you can find only the parameterization of number of parallel implementations without the parameterization of arithmetical operations. But in case if you have some project with requirements to resources equal to the possible resources for some FPGA package, we have such situation where we can implement only one parallel implementation of some project. It will be, for example, some project that will produce some computational results per one clock. So it means that we will have 2 computational results per 2 clocks. And the third part of free space inside that we cannot use. But if we will change the manner of implementation of resources of the arithmetical operations, we will use all available space and we will produce 3 computation results per 2 clocks. It can be illustrated by the idea algorithm that can be used in PGP systems and so on. But in this case, we have some number of rounds, in this case 8 rounds, that can be implemented in parallel way in 2 clocks by pair of 2 parts by 4 rounds. 4 parts by 2 rounds and 1 part or 1 component that implement 1 round with number of parallel sequential clocks of 8 clocks. So it's a good, the best implementation of this idea, but this project is still in work. The result of this work will be in few months. But the implementation of the dynamic parameterization was prepared during the development of Reed Solomon codes or some part of this code. For example, this is implementation of the lower field multiplier with dynamic and static parameterization. So, this multipliers allows to change the bits of input buses without the redesign and without the reprogramming of FPGA. So, This parameterization uses the both dynamic parameterization and static parameterization. By means of dynamic parameterization, we can select the needed database of inputs during the operation. But by means of the static parameterization, we can select the possible variance of database of inputs at the time of program of computing. So, our experimental evaluation of the resources showed that it's working. So, for example, in case of the implementation of different bits, for example, 4, 8, 12, and 15, we have only 366 logical elements. But in case if we have all range between 2 and 12, we have in 112 times more. So, we can propose the following steps of finding the needed parameters for project that was developed using these techniques. The choice some target FPGA package with some number of FPGA resources and then finding of the needed accuracy of computation and all requirements to this system and iterative search of the amount of resources needed to implement all these projects. Okay, thank you for your attention. I will answer for all questions, and I'm waiting for questions.
Do we have any questions?
I hope yes.
I like much.
Okay.
FPGAs are among my favorite
Well,
I realized that full-scale implementation and full-scale results will be due to a few months work, as you said. Because the backend side maybe there is 4 or 5 different. These are resources with very limited usage of the whole silicon chip. So the process is very small.
No.
For the whole.
Sorry, it's only example of one different component. It's the Galactic multiplier. The whole project.
It's just the element itself, not the whole project.
Yeah.
Okay.
So whole project can be placed in this package because of the requirements to the resources. It was one of the reasons of such.
The goal is to make it fit.
To make it fit not only for this package, but for all packages that can be used in the big range of the possible resources. So the main idea was in this. So if we use such technique, we can create some project that can be implemented without the changes of functionality in different range of the resources, from the lowest chips to the rich Stratix chip, for example. But by means of the changing of computational time.
Thank you, once again.